Okay, this problem we're going to be working today is going to be a little bit more challenging than some of the other centripetal force problems that we've been dealing with so far. So let's go ahead and look at the experimental setup that we have here. We're going to have a string attached to the ceiling, okay? And we're going to be swinging that object that's attached to the string in a horizontal circle, okay? So a lot of amusement park rides look like this because you'll have your object you're hanging down, and then as you start spinning in a circle, then you'll start moving further and further out on that circle. And obviously, the faster you go, the farther you're going to swing out from the center. So as long as we've got a weight attached to the string, no matter how fast we move it, and here's where some of the difficulty in this problem comes. No matter how fast we move it, we cannot get this object to swing perfectly parallel to the ground below, okay? So there's no way to get it at a 0 degree angle here, okay? So the faster we move it, the lower this angle is going to be, obviously, and the longer the string length is going to factor into that too. But the faster we swing it, the smaller this angle is going to be, but we can never get it to 0. So we're going to have to factor that angle into the problem. Okay, so on our problem here, we've got a mass that's swinging around in a circle. We have a string length of 0.9 meters, and the angle is 30 degrees. And I want to know what the velocity of that object is, or the tangential speed of the object. So obviously, we have a centripetal force type problem. And we know that the overall net force, hopefully by now we understand that the overall net force is going to be pointing directly to the center of this circle, okay? No matter where it's at on that pathway, the net force is going to be pointing towards the center, okay? Now, this one's a little bit different because if we were going to draw a free body diagram for this mass, I only have 2 forces acting on it. I've got tension in a string. So I'm going to have force tension, close enough, and we are going to have mg down, okay? And obviously, the faster I spin it, the greater the tension is going to be on that string, okay? But one thing we have to understand is that, remember, this thing is not going up and down. It's just going perfectly in a circle, horizontal, okay? So that means that any force down has to be balanced with something going up. So going up, we have the y component. We'll call this force tension y. We have the y component of the tension, okay? And then if we complete our right triangle here, we're also going to have an arrow that's pointing on the inside, and this is the x component of the tension, okay? So we have a balanced force up and down, and we can't ever get away from this mg. It's always there. So that's why we can never get it perfectly parallel to the ground, okay? There's always going to be some component to the tension. But as we swing this faster and faster, the x component of the tension is going to increase, okay? So the y component is going to decrease, or the y component stays the same, I'm sorry. The x component is going to decrease. So we're going to end up with a steeper, or with less of an angle with respect to the horizontal, okay? So we have this set up, and if you notice right here, this obviously is going to be my 30 degree angle, okay? Now, one thing that we need to know that is not given on this problem, though, probably before we get set up into this, all of our equations have radius in it. And we do not know the distance to the center of the circle because the string length is not the distance to the center. So I'm going to have to solve for that. So if I make a triangle out of this, okay, so this is my 0.900 meters, okay? If I go ahead and make a right triangle here, this side right here is going to be my radius. That's going to be the distance from here to here. Once again, I can make my triangle this way and switch this to my 30 degree angle if I want to. But since I've already got it drawn up here, I'll stay with this. Okay, so there's my 30 degree angle. The length of the string is the hypotenuse of the triangle. Okay, so we need to first of all solve for r. All right, so this is the adjacent side, so I want to use cosine function. So R is going to be equal to cosine of 30 degrees times 0.9 meters. Okay, so cosine of 30 times 0.9 is going to give me 0.779 meters. Okay, so there's my radius of my circle. All right, so at least I've got one step done on this problem. So I know the distance from here to right at the center point of this circle. Okay, next step. Now, we don't know, I didn't give you the mass on the problem either, so hopefully we understand we got to cancel the mass out somehow. All right, I don't know the tension. I know that tension Y is equal to mg. So let's go ahead and set these up. We know that tension Y is equal to mass times gravity. These two are balanced errors. We also know that my tension X, if we notice there's no unbalanced, or there's no other error that's balancing that force out. So tension X is unbalanced, and since it's pointing to the center of the circle, the force tension X is what's generating the centripetal force. Okay, so we have an unbalanced error point on the inside. So force tension X is going to generate centripetal force. So it's equal to mv squared over r. Okay, so now let's set up our trig function using the forces, and we'll kind of get a chance to see what's going to happen with this. All right, I'm going to erase this, and we know that r is 0.779 meters. Okay. All right, so once again, if I notice here, I have an equation for each one of my tensions, okay? And I've got the y and the x, so I'm going to say that tangent of 30 degrees, okay? Tangent's going to be opposite over adjacent, so this is going to equal force tension y over force tension x. Okay, so now the only thing I have left to do is sub in the two equations. My force tension X is equal to mv squared over r, and force tension Y is equal to mg. So I'm going to say that tangent of 30 degrees equals force tension Y, which is mg, divided by mv squared over r. Okay, now, sometimes it's kind of weird rearranging a formula where you have an equation divided by an equation over something else. So understand, so this is mv squared over r, but it's divided here. We can move this all the way up to the top. Okay, so we can move the r, and the masses cancel. So I am reduced down to tangent of 30 degrees equals g r over b squared. Okay, so that equation simplifies pretty easily. So since I'm solving, I want the velocity. See, I've already got the radius. I know gravity is 9.8 since we're doing this problem on the Earth. And I'm solving for b, and I know my angle. So velocity equals square root of g r over tangent of our angle, which is 30 degrees. Okay, so this really simplified down real nice, and it makes it a somewhat easy problem at this point. So 9.8 times my radius, which is 0.779 meters, okay, divided by tangent of 30 degrees, and that's going to give me a velocity of 3.63 meters per second. Okay, so that's actually not so hard once we get to this point. It's just being able to understand how the tension forces, components of the tension, will equal different variables. So once again, tension Y going up has to equal mg going down because it's not going up and down. It can't be an unbalanced force there. And the only unbalanced error then is your X component of the tension. And so since that one's unbalanced, point towards the center of the circle, we're going to set that equal to mv squared over r because that's what's generating the centripetal force. And remember, mv squared over r is still saying mass times acceleration. It's just centripetal acceleration because it's going in a circle. It's always pointing towards the center. Okay? Trying to think if there's anything else last second here that I need to tell you about this particular problem. Oh, notice what's going to happen if we change this angle. In order to make it go at a steeper angle here, we're going to have to speed this up significantly. Okay, and for example, if I was to plug this in, I guess we can do the math here real quick, but 0.779 times 9.8 divided by, if we wanted to switch this and we want to see how fast it would go just to be half of the angle or at a 10-degree angle, we'll solve for 10. We're going to have to increase the speed to 6.6 meters per second. So we're going to have to increase it quite significantly. And once again, the length of the string plays a factor in that because that's going to dictate the radius as well. So anyway, there are some other problems that we'll have to get into on an incline with an object going around it. But this seems to be one of the harder problems of the unit that students tend to have difficulty with. Okay.